I'm excited to present our ECCV 2020 work, FeatMatch, Feature-Based Augmentation for Semi-Supervised Learning. In semi-supervised learning, we're given a small set of labeled data and a large set of unlabeled data. The goal in this setting is to train a good classifier by properly leveraging the large set of unlabeled data. Consistency regularization is one of the most successful methods in semi-supervised learning. Given an input unlabeled image X, we first generate its augmented copy, X hat, by some label-preserving data augmentation. And then this method regularizes the model by enforcing consistent prediction between the input image X and its augmented copy X hat. By doing so, the model is regularized to learn a representation that is invariant to this kind of transformations. And in this process, data augmentation plays a crucial role to generate the augmented copy X hat for consistency regularization. State-of-the-art consistency regularization method relies on image-based augmentation, such as random augment or auto-augment, to produce the augmented copy X hat. However, there are several limitations of the image-based augmentation. For example, they only operate in image space, which limits the possible transformations to simple textural or geometric transformations. Furthermore, they only operate within a single instance, which fails to transform data with the knowledge of other instances in the same dataset. Therefore, in this work, we propose a feature-based augmentation to enhance the data augmentation module that is crucial to consistency regularization methods. Compared to image-based augmentation, our proposed feature-based augmentation module has the following advantages. First, it operates in the abstract feature space that transforms input data in a complex way beyond simple textual and geometric transformations. Second, it operates across instances by a learned attention mechanism to a compact set of prototypes per class. Specifically, given an unlabeled image X, we first encode it to its feature representation Fx, and also suppose we're given a set of prototypes per class, which we will describe more in the next slide. We then compute the augmented feature Gx by the learned attention mechanism from Fx to a set of prototypes. We then enforce consistency between the prediction from the original feature Fx and the augmented feature Gx for consistency regularization. In order to compute the set of prototypes per class for feature-based augmentation, we propose to use the simple k-means clustering in the feature space to extract k prototypes per class. However, there are several technical challenges to do so. First, in a semi-supervised setting, most images are unlabeled, so we don't have the label information to extract the prototypes for each class. Second, it's computationally expensive to extract features for all the images from the entire dataset before running k-means. To address these issues, we propose a memory bank method to collect image features as well as their pseudo-labels, which are already generated at each iteration of the training loop. By doing so, we avoid the computational issue of generating image features over the entire dataset before running k-means for prototype extraction. Once the training loop goes over the entire dataset, we'll pop out all the pairs of image feature pseudo-labels in the memory bank, and then run k-means to extract k prototypes per class. And then we'll update the prototypes for the feature-based augmentation module. And then the training loop will continue with the new set of prototypes. Our feature-based augmentation method can be seamlessly combined with other image-based augmentation for stronger consistency regularization. Compared with other image-based augmentation, our feature-based augmentation method is simple and effective. For example, Remix Match, one of the state-of-the-art image-based augmentation methods, they combine several advanced techniques such as temporal ensembling of the model, self-supervised loss on the unlabeled data, and distribution alignment to calibrate the prior class distribution. Despite the simplicity of our method, we achieved significant performance improvement on several standard benchmarks. On simple 10-class dataset, such as CFAR10 and SB-Chain, our feature-based augmentation method achieves comparable results with other state-of-the-art image-based augmentation methods, even though our method doesn't include all those advanced training techniques. On complex datasets, such as CFAR100 and MiniMageNet, our feature-based augmentation method outperforms other methods by a large margin. This also shows that with the proposed prototype extraction, our method is scalable to larger datasets and categories with minimum computational overhead. Furthermore, we propose a new setting based on domain net to test the robustness of our proposed method to distribution shift. In this setting, we include all the distribution data in the unlabeled set, where RU represents the percentage of all the distribution data in the unlabeled set. As shown in the table, our feature-based augmentation method outperforms image-based augmentation baseline by a large margin. This means that our feature-based augmentation method can better leverage unlabeled data when there is distribution shift. Qualitatively, in figure A and B, we plot t-SNE of feature distribution before and after augmentation. The brighter dots represent features after augmentation. As can be seen in figure A and B, a learned feature-based augmentation is able to produce augmented features that are more variable and uniformly distributed. Furthermore, to concretely visualize the learned augmented feature, we find the nearest image neighbors in the feature space and compare it to image-based augmentation side by side. As can be seen in figure C, our learned feature-based augmentation is able to augment input image to different poses and backgrounds, which could be challenging for conventional image-based augmentation. To better understand how the feature-based augmentation module works internally, we visualize the learned attention weight from the image features to the prototype features in figure B. We can see that the module learns to attend to prototype features within the same class. In figure A and C, we visualize the extracted prototypes. In figure A, the diamond shape represents prototype features overlaid on the image features in t-SNE plot. And in figure C, we find the nearest image neighbors of prototypes in the feature space. We can see that our method successfully extracted a great variety of prototypes per class. If you're interested, please visit our project page and our ECCV presentation. Thank you.